Hello, everyone. Good morning. Welcome to Saturday Morning Astrophysics, or SMAP. My name is Ethan, and today we're going to be taking you through the realms of galaxies with our special guest hosts from Purdue, Professor Kyung-Soo Lee and graduate student Vandana Ramakrishnan.
Yeah. Hi, everybody. Good morning. As Ethan said, I'm Vandana. I'm a fifth year graduate student at Purdue University. Um, I work primarily, as you might be able to guess, I work on galaxies, specifically very distant galaxies, and also the group, like clusters of galaxies, which are hundreds and sometimes thousands of galaxies all grouped together. I'm really excited to tell you more about galaxies today because, in my not at all biased opinion, they are very, very cool objects, right? And yeah, so I hope you enjoy. So, first of all, I would like to ask all of you, what is a galaxy, in your opinions? If you had to explain this to someone back in the 1900s when they didn't really know what a galaxy was, what would you tell them? What is a galaxy? Please go ahead and say it out loud.
I think I would say that a galaxy is a huge collection of stars, stars in solar systems, planets with their host stars. And typically, I'm pretty sure in the Milky Way, at the center of our galaxy, I think we have a supermassive black hole.
Yes, that is an excellent and very comprehensive answer. Thank you. So, yes, that is correct. Galaxies are huge collections of stars. And as you said, hundreds and thousands and millions of stars, in fact. Now, what may be a little surprising is that all galaxies, no matter what they look like, are basically made of the same materials. Would anyone like to guess what those materials are?
Like stars and gas.
That's right, stars and gas. Anything else? Yes, Naomi.
Also a lot of like gas and dust.
Yeah, and dust.
Maura, do you have any ins any insight on this? Any other things you think are galaxies are made of?
I would just probably go along with what everyone else is saying: stars, planets, dust, clouds, gas. Yeah.
Well, yes, as everyone said, galaxies are made of stars. That's probably the obvious one. Dust, gas, and what's not maybe immediately obvious because we can't see it, dark matter. And you can kind of see these in the two images at the side. The blue bits, the really pretty blue bits along the spiral arms, those are the stars and gas. The brown, that's the dust. And way towards the center of M81, as was stated by Akhil, you have the supermassive black hole. Dark matter, on the other hand, you can't see it. Well, that's where its name comes from. But that doesn't make it any less important. In fact, by mass, dark matter is the dominant component of galaxy. It weighs more than everything else in the galaxy put together. So, okay, now we know what a galaxy is and what it's made of. But why should we care?
To see if there's life, like in their places.
Definitely, that's definitely true. But why would we think there might be life in other galaxies?
Because there's life in ours.
Well, yeah,
Oh,
that's basically what it comes down to, right? One
yeah.
big reason to care about galaxies is because we live in a galaxy. We live in the Milky Way. And you can see the Milky Way here stretched out along the sky. It's quite pretty, isn't it? You can actually see somewhat the dust lanes here as well, the stars in the dust lanes. It's lovely, but it's not very much like the pictures I showed you in the first few slides, is it? So why does the Milky Way look so different? Yeah, Naomi.
No, just because because we don't have the same perspective on it, because we can just see part of it since we're in it.
Yeah, exactly. We can't see all of the Milky Way because we are inside the Milky Way. We are in a very, well, I hate to say it, but we are in a very unimportant neighborhood of the Milky Way, all the way off towards one of the edges in the spiral arms. But that may actually be for the best. So in the image to the left, you can see a zoom in towards the core of the Milky Way. And as you can see, that place is jam-packed with stars. You have like stars galore. And not only that, you have a bunch of very young stars, which frequently explode as supernovae. You have the supermassive black hole. In other words, the core of the galaxy is a very violent neighborhood, to say the least. You have energetic events happening there all the time. It's not exactly conducive to life. So, maybe we're fine where we are. The Milky Way is, in the grand scheme of things, not a very unique galaxy. We have a lot of galaxies that look like it. If you guys had to guess, what do you think these galaxies as a collective are called? This is like, how are they classified?
Spiral galaxies.
Yeah, spirals, because, they look like spirals. Then we have the other group of galaxies. What do you think these ones are called? Kendrick.
I think they were called elliptical galaxies.
Exactly. Spirals and ellipticals. These are the two main classes of galaxies. So way back again in the 1900s, when people first started realizing that, those blobs we can see up there, those are actually whole other galaxies, just like ours. Back then, Hubble actually classified galaxies into ellipticals and spirals, and he built a pretty involved model, which is what you can see in this image here. All the way on one side, you have the most the most elliptical of the ellipticals. They're like very round and neat looking and compact. And then as you head towards the right, you have them getting progressively more and more eccentric. That's what we call it, like where the ratio between the axes is more and more different. So you go from very circular to more and more elliptical, and then you get into the spiral galaxies, right? The spirals themselves are split into two groups, some which have a nice little bar at the center, those are called barred spirals, and the ones without a bar, those are the normal spirals, right? But regardless of whether they're normal or barred spirals, all spiral galaxies have a very pretty and neat, well-developed disk. So, quick question. Do any of you, the Milky Way is a spiral galaxy. You have probably gathered this from the images at the beginning. But do you know if the Milky Way is a normal or a barred spiral? You can just guess.
Barred.
Yeah, it is in fact a barred spiral galaxy.
Hey, Vandana, I have a question real quick. Did we know about galaxies before we had telescopes?
Well, not really, because from the ground, galaxies, they just look like blobs or like little points. Because most galaxies, they are so far and distant from us that we can't, with the naked eye, make out their shapes and structures at all. So that's why it was only in the 1900s that people began to realize this, even though, technically we have been staring at the sky through all of human history.
Thank you.
Yeah, if anyone asks, I am very proud to be an astronomer because it is one of the oldest branches of science to exist. So disk galaxies, right? We live, of course, in a disk galaxy in the Milky Way. But when you look at other disk galaxies, what you see actually depends very much on how you're looking at it, on your perspective, right? Because these are not symmetric, not like ellipticals, which basically look the same no matter how you look at them. For a disk galaxy, whether you're looking at it edge on or face on, that makes a big difference. Of course, the face on galaxies, you can make out the structure of the spiral arms very clearly. That's nice. And so you can study the individual components of those galaxies very well. On the other hand, in the edge-on galaxies, a lot of the starlight is blocked out by the dust. But we can still learn something very, very cool from these edge-on galaxies. Quick question. When you look at these spiral arms, right, in the face-on galaxy, how do you think the spiral arms hold themselves together? Like, why do we have spiral arms? Why aren't those galaxies why aren't the stars all just falling towards the core and becoming one giant blob? Why?
Because they all like have inertia, and so it's kind of like how the Earth orbits the sun. It doesn't like crash into the sun, it just orbits it. And also there's like a black hole in the middle of it. So that's holding it together.
Yeah, exactly. So stars are orbiting in galaxies in the same way that planets are orbiting around the sun, right? So these spiral arms, the stars in these spiral arms, they are all rotating around the center of the galaxy. But how do we know this? Like, is there any way to get more information about the motion of the stars? Well, this is where the Doppler effect comes in. Does anyone know what the Doppler effect is? Yeah, please tell us.
So in context of light waves, so if the object is moving away from you, the waves would get longer, and so that would be redshift. But if they're moving towards you, they would get like compressed, and that would be blue shift.
Exactly. I mean, you've taken the words out of my mouth, right? So this is what a moving object emitting waves looks like. Because it's moving from point to point as it emits these circular wave fronts, you can see that the waves in front of the object, they're getting all compressed, and the ones behind, they're more spread out. And yeah, in terms of light, more compressed, shorter frequency, that's blue. In behind, more spread out, lower frequency, that's red. So when you look at an object, if it's moving towards you, it's red. If it's moving away from you, I'm sorry, when it's moving towards you, it's blue. When it's moving away from you, it's red. So when we look at a galaxy, right, what can we learn from the Doppler measurements of the stars? Hashini?
We can tell how far it is from us.
Well, yes, that's definitely true. By looking at the redshift or blue shift, we can tell how far away a galaxy is from us. But and that is a very useful measurement. It's very important to know. But in the context of this motion of the stars in the galaxy, what can we learn from the Doppler effect?
We can tell if it's moving away from us or toward us.
Right. So we can tell if it's moving away from us or towards us, right? And what that means is we can measure the rotation of the galaxy. And more importantly, we can measure the speed of rotation of each one of the stars in the galaxy, right? And so in this case, you can kind of tell the direction of the rotation from the way the spiral arms are arranged, right? When you're looking at the galaxy face on. Of course, you can't tell that for an edge-on galaxy, but you can still make out how it's rotating from the Doppler shift of the stars. Another thing you'll note about this edge-on galaxy is how thin it is. And coming back to the poll question at the very beginning, in fact, if a galaxy was scaled down to the size of a pizza, its thickness would be a few millimeters. That's about the same thickness as a coin. So very much thinner than even the thinnest crust pizza. In fact, the motion of galaxies is where you get the biggest difference between the spiral and the elliptical galaxies. In the spiral galaxies, the motion of the stars, it's very organized. These arms are rotating around the center in a very, very uniform, like unified way, right? But in the elliptical galaxies, stars are just moving all about the place at random. So that's where you get this cloud-like or blob-like shape. But in fact, I said earlier that the two main classes of galaxies were the spirals and the ellipticals. But that's not quite the truth. There is another shape of galaxies, right? And that comes from what happens when two galaxies collide. What do you guys think it would look like if two galaxies were to collide? Yeah, Apurva?
Sort of an irregular shape, sort of like dust, if that, I don't know if that makes sense, but it would not be like an organized, like elliptical or spiral shape. It'd just be stars floating around.
Yeah, that's exactly right. So when two galaxies have like a flyby, right? The gravity of one galaxy starts affecting the stuff, the stars and dust in the other galaxy. And so these galaxies, they basically start unraveling, right? And so you have these plumes and tails of matter between the two galaxies forming bridges. So this is a simulation of what it would look like if two galaxies were to collide, right? It's not real data, but it's interspersed with actual images observed by Hubble. So these merging galaxies are something that you see very often, or not very often, but it's certainly something you see often enough in the universe. And yeah, personally, I think these galaxy mergers are very, very beautiful. Like just watching how they kind of swirl around each other. It's kind of like a dance, isn't it? It's very pretty. And it might interest you to know that our own Milky Way galaxy, it's destined for a collision with its nearest neighbor galaxy, Andromeda, or also known as M31, in about 4 billion years. So, it's not really our problem. None of us are going to be around to witness the grisly end of our galaxy, but it's going to happen. So it might also interest you to know that sometimes when these galaxies start interacting, just by the interactions of these galaxies, new star formation can actually be kicked off. And you can see that in this image here, right? The red bits, the image to the left, the red bits, those kind of indicate where there's new dust obscured star formation going on. And up towards the top, you can see a slightly more minor merger, like the one Sue mentioned has happened with the Milky Way. The Hubble galaxies with a settled Hubble type, these spirals and ellipticals, they haven't had a merger in a very long time. And that's why their shape has settled very much. But most galaxies probably have undergone a major merger at least once in their life. So now that I have told you a little bit about galaxies and their various shapes, it is your turn to go hunting for your favorite galaxies. And the way we're going to do this is with the Legacy survey. So you can go ahead and open that on your browsers. So this is just a snapshot of the Legacy survey. Hopefully all of you are seeing this on your screens or something similar. So you can kind of ignore the bits off to the right. The main things we're going to be concerned with today are the zoom in the upper left and the position on the uppermost left. I will show you in more detail in a second. Okay. Yeah, so this is the Legacy server. And again, I hope all of you are seeing this on your screen. My suggestion would be to minimize these two boxes just so that they don't get in your way. So the first thing, zoom. You can just zoom using this panel here. Zoom out or zoom in. The second thing, to move along in this image, just drag with your mouse. Here's a pretty galaxy. Now, if you find a pretty galaxy and you want to recall its position for the poster, hover your mouse over the galaxy. And you can see two numbers at the top left, RA, dec, right? This stands for right ascension and declination, which is basically the exact same as latitude and longitude, only in the sky, right? It just tells you where in the sky you are. So the right ascension of this galaxy is 133.9046, and its declination is minus 3.0541. So just note down those two numbers, and then that will help you find that galaxy later. One more thing, if you have a favorite galaxy already, one you know about, then you can just, and it's a named galaxy. If it is a galaxy with a name, you can type that name in here, jump to object, and just hit enter. And it will take you right there. So before we head to the breakout rooms, any questions?
Yeah, Gio?
Yeah.
So if you were to find a galaxy and you wanted to find it again later, and you have the coordinates, how would you do that?
So you can do the same thing. You can input the coordinates here. in jump to object. It doesn't have to be the name. You could also give the position. So type in the right ascension, space, declination, and it will take you to the coordinates you input.
May I just interject here for a minute? Our final goal will be for you to look at some galaxies, and in the end, find your favorite galaxy. So find one that's particularly interesting to you, and then we'll ask you to put those coordinates in the chat, and we can look them up later and provide the images. And then we're going to create a poster, something kind of similar to what we did with Cassiopeia A last time. And so we'll take your favorite galaxy images and make a poster and identify them by your name and or the name of the poster or the name of the galaxy. And then we'll send that to you. So if I don't have it already, I'll be asking for your mailing address so that we can send you the final product.
Can I comment one thing?
Sure.
I think Samarth also had a question, but so one thing that I wanted to suggest to everyone is that because universe is a really big, vast place, that what that means is that most of the galaxies are pretty far away from us. So they're gonna look very small. So the kind of nice and big galaxies, which are only big and and nice looking because they're pretty close. So what that means is that if you want to find your favorite galaxy, which better not be a little dot, right? So you may want to zoom out a little bit so that you can see a big chunk of the sky at a time. Because I think, Vandana, maybe you want to zoom out a little bit more. So I would just zoom out, maybe not too much. You should be able to still see enough, but you don't want to zoom in quite a bit and then start moving around in the sky. You're not going to be able to get very far.
Can you move the map down?
Move back down.
Yeah. And to the right a little bit. Yes, yeah, stop. So is this a galaxy or a star?
Oh, that. No. So this is it's a star, right? If you're wondering about these red lines, basically what happened here is this is a compilation of really deep data. Like they pointed the telescope at the sky for a really long time with the intention of detecting faint and far away objects. But that means that the really bright and nearby objects, like stars in our own galaxy, those basically we got so much light from those that the detectors got overloaded. It's called oversaturation. So the light kind of spilled out of those pixels and along these trails here. So yeah, these are stars. And these red lines, those are image defects. It's not a galaxy.
Those stars are in the Milky Way. So we're looking at galaxies way off in the distance, and then those stars are in the foreground in the Milky Way.
If you're scrolling through for a while and you can't find a specific galaxy you're looking for, or you just can't find much that's very clear, if you refresh the page, sometimes it'll land you directly. It tries landing you directly on a galaxy or larger object.
And you can always go to a named object. So the Messier galaxies, M31, M81, M87, all of those are always an option.
Okay, so does anyone else have any questions before we go out into the breakouts?
Yes. So I'm like just exploring right now, and the more I zoom in, the more like pixelated it gets. Like when you see those like old TVs and you get the colored dots, like tiny dots.
Yeah, that's kind of unavoidable. Because like you said, you're coming closer and closer to the pixel scale, right? Like the more you zoom in, the more the individual pixels become clear. Which is another reason it's better to choose a slightly bigger object that you can see while you're a little bit zoomed out.
Okay. I was just curious about what it was.
I did want to show you guys one object that I found. This is a merger of galaxies. You see, we have two big bright clusters of stars here, right? And how do I know that? It might be a little bit ambiguous. If you guys click on the object and click look up in SIMBAD, you get a list of all of the different objects that are in this picture, and you can hover over one and it circles and it gives you the name of that object. And so the main object here is NGC 3664. And I click on that and it tells me it's a galaxy in a pair of galaxies. So we can assume that it's probably an interacting galaxy. So if you're struggling to figure out, okay, is this like an interacting or merging galaxy? You can kind of get information on that using this. Anybody have any cool galaxies that they want to talk about?
I just have a question.
Yeah.
When we're putting in the coordinates for the galaxy, do we have to put in the zoom as well or no?
You don't have to. I mean, if you're just looking at the galaxy, so we'll try to kind of fill this out as a group too while we're working on this or during this breakout room. So if you find one that's cool that fits like any of these descriptions or is just an extra galaxy, we can put it down here. Yeah, do put it in the chat. Or you can put the name in the chat, the name of the galaxy in the chat if you look that up as well. It's up to you.
Yeah, I think we're to just like specifically clarify. I do think you only need to put in the RA and declination. You don't need to put in like the zoom level. You can always like zoom in. We'll zoom in for you. We can kind of just adjust as we go.
Mm-hmm. Yeah, the RA and dec, those coordinates are designed to be as specific as possible. You can go out to as many decimal places as possible you need in order to locate the exact location of that object. So whatever is displayed right here should be good. And you can click on that and copy those numbers as well. Yeah, good question.
Amelia, do you want to show how you can get rid of the menu box to the right just to see more sky?
Oh, yes. Do I click on this and this? There we go.
Yeah.
Click on the little minuses next to those words there so you can see more of the sky. Anybody have any cool things that they found? Naomi?
I did just find the triangulum galaxy. I can put the coordinates.
Ooh, yes.
Chat.
So I put the Naomi's object coordinates in the chat. Jump to object. Boop. Woo! It's
Oh,
big.
wow. Look at that.
Yeah.
So anyone have a guess what type of galaxy that one is?
Seems like some kind of spiral, but can't tell from the picture if it's barred or not.
Yeah, I would say that's a solid guess. I'd say, I don't know, Amelia, what do you think? Probably not barred.
Probably not barred. I mean, we can look it up. Galaxy. Didn't spell that right at all. Yep, just a spiral galaxy. Yeah, good job. So let's put those coordinates in on face on spiral, right? Because it doesn't look like a straight line or it doesn't look flat-ish. It's we're looking directly onto the whole of the galaxy, right? Let's put that in there. This is the triangulum galaxy. Big.
And then Matthew put his coordinates in the chat if we want to jump to that one afterwards.
All right. Absolutely.
Matthew, do you know what zoom you were at when you were looking at this one?
Is it one of these?
Yeah, just like all three of them.
All three of them, yeah. What do you think we're looking at here?
Either three galaxies that just look like they're close because of perspective, but they're actually far away, or maybe like a galaxy cluster.
Mm-hmm. Yeah. A lot of times galaxy clusters will be so big that they could just look like they're overlapping here, or There's just a general part of the sky where there's a lot of galaxies. If you look at a huge map of the sky, it's kind of hard to say specifically where a galaxy cluster is, but you can say, okay, in this general region, there's a high density of galaxies. So that's a good inference right there. I would say probably these are just overlapping. It is probably a perspective.
It almost looked like a merger, I thought, but
yeah, I think so. There's a bridge and then there's a tail. Remember that Vandana was showing a couple of systems that look like there's a bridge between the two galaxies, and then you have a long tail that move away from the other galaxy. So that's a classic sign of merger.
Yeah,
that specific one. Look at how that the spiral is distorted to make that bridge.
Oh wow.
Oh yeah, that's nice.
That's a good one.
A lot of blue, very blue.
Yeah, let me record that. Yeah, one strategy I can recommend to find something cool, which is how I found what I did, is just zoom out as far as you can go, kind of wiggle your mouse around a little, and wherever it lands on, just zoom in and see what you can find. Found that already.
Isn't that what we had before?
Yeah, it looks like one Samarth found.
Alvina, this was yours, right?
Yeah.
That's cool. That looks like it very easily may have interacted with something in the past. Let's put that one on there too. Let's do another. I'm going to just change this to another favorite galaxy. We have Messier 106 from Hashini. Let's look at that one too. I think we can just put it straight in here.
That was the one I showed before for my favorite.
Okay. Yeah. Very nice.
And then Matthew, do you want the one you sent before to be your favorite, or do you want to find another one, or?
Yeah, I like that group of 3 galaxies.
Sick.
Let's look at that real quick. Let me make sure I have it written down so we can get it on the poster.
Does anyone have any questions about what went on, or anything?
I had a question. I think earlier we were talking about how because of the Doppler shift, we're able to determine the speed, like the speed of the rotation of galaxies. In that same sense, is that how like physicists and astronomers are able to measure like the torque that galaxies have?
Yeah, essentially. So you know that the galaxies are rotating, right? So the ones that are coming head on towards you and the ones that are heading away from you, like, you know, their so basically what you're measuring is their tangential velocity, right? And from that you can figure out.
Yeah. Does anyone else have anything they want to get off their mind or ask? You have some professionals here. It's a good place.
I had a question. So this, I don't know if it's going to make sense, but so Kepler's first law, that applies to planets, states that like they all have elliptical rotations around the sun. So I was kind of wondering, like obviously that's 4 planets around the sun, but I was wondering if there's any rhyme or reason to that in regard with galaxies, like if that affects how objects rotate in galaxies, like for the Milky Way around the black hole. Because obviously like they still have different shapes, so not all galaxies are shaped as ellipses. So
Right. So it's basically like, you're exactly right, by the way. The rotation of stars around the Milky Way's black hole, it's basically elliptical, right? The thing is, what we're kind of seeing is the aggregate of all the stars in the galaxy, right? So in a spiral galaxy, all of those elliptical orbits are kind of aligned in a similar way, and that's why you see that organized shape. Whereas in an elliptical galaxy, all of those elliptical orbits are randomly oriented, more or less, right? And yeah, this kind of came up in breakout, but in fact, the way they discovered the black hole at the center of the Milky Way, Sagittarius A star, was by looking at the orbits, the elliptical orbits of the stars rotating around it. So just by looking at those elliptical orbits, they could kind of infer the mass of the thing they were rotating around. But they couldn't see anything there, so that's how they guessed it was a black hole. A really, really big black hole.
If I can add one more thing to Maura's question is, so I think the main difference between how our planets move around our sun as opposed to how the stars move about their galaxy center is that our solar system is very empty, right? So we have 8 planets, and then in the middle of it we have the sun, which is much more massive than anything else, including the biggest planet, which is Jupiter. So basically all they see is the sun's gravity, and then that's why they go around in elliptical orbits. Stars in a galaxy, of course, same principle applies, but then there's a lot of other stars that some of them are pretty close to that star, that sometimes the stars may see the gravity of a nearby star much more strongly than what it sees from the galaxy center. So it's not it's much more crowded place where a lot of different stars and objects experience gravity from each other as well as the center of the galaxy. So I think that's maybe the main difference.
Samar, go ahead.
Are binary systems common?
Very common. There's this statistic about the percentage of stars that are in a binary. I don't recall it offhand, but I think a lot of, is it the majority?
More than half.
Yeah, more than half of the stars in the galaxy are in binary systems.
But I couldn't really find any in Legacy survey.
Binary systems of galaxies are less common. So you have, of course, those mergers, galaxy mergers. Well, okay, first of all, binary systems of stars probably wouldn't show up as 2 distinct stars in Legacy survey. I don't think the resolution is enough for that. That's probably the case, right?
Some of them may just be so far away from each other that they just look like 2 stars. You cannot really, you have to look at their motion to see that if they're going around this way, right? So what you see in the Legacy survey is a snapshot of one time at which those stars are found. So even if you're looking right at them, you wouldn't be able to tell. And then the closest one, as Vandana said, that they might just look too close that they may look like 1 star.
Naomi?
So, and I know there's nobody really knows yet what exactly causes spirals to be spirals, but is there something that determines whether spiral is just a normal spiral or whether it's a barred spiral?
It's a little bit difficult to explain. So the spirals, so we think that most galaxies start out as a spiral galaxy. And that's because the way that, what you see as a galaxy is a collection of stars, right? And the collection of stars are made of gas. And so in the universe, things are moving in some direction, some of them come together, and, most of the time what happens is that the gas, that which would grow to be a galaxy by forming stars out of those, they're gonna just start rotating in some direction. And I think one of you said earlier that the same thing as why the Earth is going around the sun. So there is this inertia, which we call the angular momentum, that that basically make it keep going around instead of falling directly into the sun. So something like that is happening for the stars that are born from this gas cloud. So that's why they look like a disk galaxy. So spiral galaxies are disk galaxies with some area that has more stars than others, which we see as spiral arms. The barred spiral, that's a little bit more difficult to explain. So spiral galaxy has a disk, but you've probably seen from the Legacy survey and the pictures that you've seen before that Vandana showed you, that there is something in the middle, which we call bulge, that kind of looks like a mini elliptical galaxy in the center of a disk galaxy. And some spirals have a bigger bulge than some other spirals, but they have it there. So you have a different component bulge, and then you have a disk, stars that are on the disk. There are some stars in the bulge, and there's some dynamic interactions that sometimes make a bar. That basically some of the disk stars will migrate into the center and then form a bar. But I don't think I can explain that beyond that, what I just said.
Before we go, I would like to thank our guests today, Vandana and Professor Lee.
Ethan, I'm going to ask one more question before you actually wrap up. And that question would be directed to Professor Lee. Professor, you're engaged in research, you have a distinguished career, you're a professor, you've just made discoveries, you've done some great accomplishments in your life. At some point in your life, there was probably a spark that started your path to your current, to what you do. Where your interest in astronomy and astrophysics. Can you tell us where that spark came from? What was the turning point in your life where maybe you thought, this is what I want to do?
To tell you the truth, I don't know if there was a single moment at which the spark just ignited. But one thing I'm sure is that it happened around the time that I was your age. So I was reading up a lot about the universe, Einstein's special relativity, about black holes. I think I read Stephen Hawking's a book or two. And, I was just interested in things that are, happening out there, and everything that I was learning about the universe made everything that, happens around us on Earth just seems almost insignificant. Of course, it's not insignificant, but everything was such a grand scale, and I think that's what fascinated me. So I think no matter whatever you end up studying later, I think you just have to pursue it and then try to keep asking questions and keep reading another book that pique your interest, and I think that's probably you're gonna land in the right place. Just stay curious.
All right, thank you very much. I know we're a little past our scheduled time. I just wanted to thank our special guests today, and thanks to our TAs. Thank you all very much again for coming out to the Realms of Galaxies SMAP session, and hope to see you at the next. Bye-bye.
Bye. Thank you. Bye.
Bye.
Bye.